All right, thanks. So I want to start with Immanuel Kant in the Prolegomena, which was 1783. He said that space has 3 dimensions and cannot have more is built upon the proposition that no more than 3 lines can cut each other at a right angle at one point. So pretty much what he's saying is that space has to have 3 dimensions, because if you have a point, you can only have 3 lines that intersect at a right angle. So the reason I brought this up is because it's fun to shit on old philosophers. And he's totally wrong. So first off, why a right angle? Like, that's totally arbitrary. Second, couldn't there be more that we can't just visualize? He's like, he's stating this as a logical proposition when really he's using his own sense of vision. And also, just what? So we want to look at a more abstract notion of what exactly a dimension is. So what is a dimension? Well, it's an attribute. Oh, sorry. It's an attribute of space it's an attribute of space or an object. That's not the actual definition of a dimension. If you thought I was going to stop there, like, I'm sorry. So a space, we're left with the question, what is this? And then an object, what's an object really? It's just a thing that doesn't not exist. It's a thing, so that could be anything. So let's look into spaces a little bit more. I need to grab these. So a space is a thing that has operations. Examples of operations would be like vector addition, or unions, or intersections. So these exist within a space. And then we also have a thing called proximity relations. And this is something like neighborhoods about a point, or you have the notion of distance or convergence. And then you have symmetries. And symmetries are really interesting. So we're going to go into these a little more in depth. So symmetries, really, generally speaking, are transformations that preserve structure. So I'm going to give some examples. First, a boring example of y equals x squared. Well, this is symmetric about 0, because it's the same on both sides. OK, a slightly less boring example would be a matrix A is symmetric if it's the same as A transpose. Or perhaps that's even more boring. But let's get into a more exciting example. So symmetric groups. Raise your hand if you know what a group is. OK, 50-50. We're going to go over the definition then. A group is another abstract object thing. We're going to spend a lot of time with those today. But really, it's a set. And it's got a binary operation, levitating dot. And this binary operation acts on objects in the group. And it has a couple properties. So let me state this a little more clearly. A group is a set with a binary operation, and this binary operation has a couple properties when applied to the objects in the set. So one of these properties is that the binary operation is associative. OK? We can move parentheses, no problem. Another attribute of a group is that we have this thing called an identity element. And what the identity element is this thing where when we apply the binary operation to any object in our set, nothing happens. And we can do it the other way around, and still nothing happens. And then the last property of a group is that for any object in the group, there exists an inverse object in the group such that when we perform the binary operation on those, they become the identity, and you can flip them around. OK, so that's a group. OK, so there's a thing called a symmetry group. And there are symmetry groups of Rn, or like n-dimensional Euclidean space. So I'm going to erase this. And I'm going to define a symmetry group. So we have the symmetry groups of Rn. And what these are defined of is a subgroup of a group of isometries on Rn that fixes a finite amount of points. And I don't expect this amount of points. I don't expect this to mean anything to you right now. This doesn't need to be finite. Thank you. It fixes a set of points.
OK.
Thanks, Jeff. Good catch. OK, so what this means is that we have some transformation that's moving things. It can be moving objects, and certain points of the object that's moving will stay the same. So let's go into a specific example. And actually, to get to this example, we have this nifty little theorem. And I have no clue where this theorem came from, but it's true. So the theorem from nowhere. Only finite, this is where I got mixed up. Only finite symmetry groups, little m there, in Rn. The only finite symmetry groups we have in Rn are the integers modulo n with addition, and then this group called Dn. And once I show you this group Dn, this is going to make a lot more sense. So essentially, what it is you have a polynomial. So think of like examples of a triangle. So this is your object. This would be like A or B in the group. And the operation, our binary operation, is rotations of this. So you can have a rotation that's 120 degrees, or 240, or just 360, or you could have rotations back. And these are your operations.
Reflections, yes.
OK. And then reflection. So these are all transformations where you have these points that remain exactly the same. So pretty much the object looks the same after you perform the transformation. And we can think of that as a symmetry in the same sense that this is a symmetry, which is cool and abstract and weird. So can we think of Dn as a space? Well, it doesn't have proximity relations or it doesn't have neighborhoods. So womp, 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 it's not. But let's go into an example of a space now. So we're talking about spaces. Let's go into a highly strategic example of a space. And what this is a vector space. Yeah, question? Yeah, OK. So we're talking about vector spaces. How are we doing on time? OK. So a vector space is a field, which you can just think of a field as like a set, like a group has a set, but it's got addition, multiplication, division, and subtraction, like you would expect with the real numbers. So there's a field. And also, a vector space is defined over the field. It's not the field itself. It's defined over a field. And in this case, it's defined over the field R, the real numbers. Cool. So we have objects in this space. Oh, I shouldn't have erased the definition of, or never mind. OK. So the objects in our vector space, does anyone know what they are? Vectors. Little vectors. And then the operations, this is actually not as straightforward. So we have addition with vectors. And then we have multiplication, but with scalars. So A in R, and then B in our vector space, A times B. OK. People are nodding their heads sagely, so I think everyone's getting it. So a key note here is that if A is in R, that does not mean that A is also in our vector space. And this comes from V being a vector space over a field. Let's go into the nuts and bolts of what makes a vector space. And we have 8 of these. So the first is associativity. Pretty much this means that U plus V plus W is the same as U plus, oh, I wrote that the wrong way, but regardless. Once again, we can move the parentheses. And this is for vector addition. And then we have commutativity, which means V plus U is the same thing as U plus V. The third that we have is an identity element. Oh, and let me say, we have an identity element under addition. So this is going to be in the vector space. So for all V in our vector space, V plus I equals V. Can anyone hazard a guess as to what this identity element is? Some crazy mind-blowing stuff. It's the 0 vector. OK, and then we have an inverse element. So for all V, there exists a V, a negative V, really. All right, cool. And then here's where it starts getting more interesting. We have this thing called compatibility of scalar multiplication and field multiplication. So what that means is AB times V is the same as A times BV. Mind blown. And then we also have a multiplicative identity, which is a little less exciting. And then I is in V for all little v's in V. OK, we're getting down here. So distributivity of scalar multiplication. This is another one that's a little more interesting. So if we have A times U plus V, this is the same as AU plus AV. So this all may seem really simple, but why this is interesting is because some dude sat down there and thought we need to make all of these assumptions, and that person enumerated all of these assumptions to build up a vector space. So what we're doing is really interesting right now because we're building up the assumptions necessary, or rather the axioms necessary to define a vector space as well. And a lot of more interesting stuff is going to fall out of this. So bear with me. Which is distributivity of scalar multiplication with respect to field addition. So this is kind of similar to the other one, which is it's just if we apply addition to the scalars, then it will multiply out when we apply it to the vector.
Linear transformations of matrices.
Yeah, just think of vector addition and scalar multiplication. That's all we have right now.
You're jumping ahead.
I and
Usually find identity elements.
on 6, it should say I and R. Not that one.
Oh, thanks, guys. Okay, cool. Everything on the board is now perfect. Take a picture, I'm sure. Okay, so a little fun fact is that our vector space can be defined over, we defined it over R, but it can also be defined over the complex numbers. So we're not going to do anything with that, but so little fun fact, nugget of candy. Okay, so we know what a vector space is. Let's define actually the dimensionality of a vector space. So let's say we have this set, and it's a set of vectors, vi all the way through vk, and all of these vectors are in our vector space. And these vectors are made strategically. We know that for any other vector, va, in our vector space, actually va could be one of these. Doesn't matter. For any vector in our vector space, va is a combination, a linear combination of these things. So it's going to be like, yeah, we'll call it a1 vi plus a2 vi plus 1 plus yada yada ak vk. So we have this set. And as a matter of fact, we could make a shitload of these sets. OK. Cool. So the dimensionality of this. Oh, I already wrote dimensionality. I'm just getting redundant here. This is the minimum size of this set. Is this intuitive to anyone in this room? This definition, besides Jeff? OK, yeah. And so let me give you a clue that'll lead to some actual intuition. Is these are the basis vectors of the vector space, and what this is us saying that those basis vectors span the space. So what we're defining the dimensionality of our vector space as is the minimum number of basis vectors required to span the vector space. I just got goosebumps. I really did. That's dorky.
Is it the min or the in?
Oh God, are you talking about like the inference or the inductive?
Or is there an assumption of finite dimensionality?
Oh, no. Maybe. I don't know. I didn't deal with that case.
You're implicitly, you have an implication that that set's finite.
I guess if there's a min, yeah.
If you're going to talk, yeah.
What's the min of an infinite set?
Yeah, you don't want to deal with finite, or with infinite dimensions.
Or I guess you could go by cardinalities of an infinity. There we go. The minimum cardinality of infinity required to. Yeah, let's just assume this is a finitely dimensional space. Yeah. So a dimension in general. Here's the meat of it. It's the minimum number, and this is like, I'm going to show you in a second that there are a lot of different ways to define dimensionality, but this is like the conceptual notion of dimensionality. It's the minimum number of data points that's required to differentiate any two possible points. I'm just going to read it to you, then I'm going to write it down. So it's a minimum number of data points required to differentiate any possible pair of points, A and B, in our space. OK, so to differentiate any possible pair of points, A, B, in our space of S. We'll write that down. And you can think of data points as, or the minimum number of data points really as the minimum number of coordinates. So we can give an example here where this becomes kind of wonky. If you have a cube and you have points on the surface of a cube, then you can think of that point as just an XYZ point. And then you'd say, oh, the dimensionality of the surface area of a cube is 3. Wrong. So it turns out that what you can do is actually just define it via an X and Y point. And how you do that is you take the square in this direction and treat this as like this would be x equals 0 and maybe this is x equals infinity, or you could just make it this is x equals 100, and you go along this line. And that tells you whether, if we'll say this is y and this is x, then the first coordinate, this coordinate, is associated with a value between 0 and 100, and that tells you where along this perimeter you are. So like this is 25, this is 50, 75, there we go. And then you can also take this square here and associate this point with 0, and then right before it with 100. Let's not deal with fringe cases of like infinite closeness. 25, you get the point. So any point on the surface area of this cube can be represented with 2 coordinates, which means the dimensionality is 2. All right. Gen's nodding his head in excitement. So I don't know. I came up with that last night. I just thought it was really cool. So we have this thing called an algebraic variety. And pretty much what it is a set of solutions to a system of polynomial equations. And pretty much what a system of polynomial equations is, well, let me just give an example. So say we have functions 1 through function n. And all of these functions are polynomial functions. So we can write this as like f of 1 equals an xn plus an minus 1 xn minus 1, yada yada, up to our constant.
Are they all polynomials of degree at most n? Or a degree at most something?
It's a finite set.
I don't know.
It's a finite set of functions, but could I have like a Taylor series in there?
Oh.
Polynomials. These are polynomials. You cannot have a Taylor series.
Okay, by definition. Okay, sure.
Yeah, definitionally a polynomial. A single polynomial has a maximum.
Jeff to the rescue. Okay, so what we do then is we set all of these equal to 0. And when all of these equal 0 at once, we take the set of solutions to these. So it's going to be the x's, any x value, such that f1 through fn equals 0 at the same time. And when these equal 0, that is an algebraic variety. Okay. Yeah, so algebraic varieties are a space.
Okay.
And yeah, that's really key actually to this. Go ahead.
So it's the set of all x such that that's true.
Yes.
Okay.
Ah, yes. Thank you. Okay, so how would you define the dimensionality of an algebraic variety? I'm going to keep you on your toes for this one and go through an example, and then we'll get to it. We define a polynomial, and then we have a bunch of polynomials. We set all the polynomials equal to 0 at the same time, and then there are some x's such that all of them equal 0 at the same time. We take the set of all those x's, and that's an algebraic variety.
Right, so you want to know the dimension of this?
Of this set of solutions. Of these x's,
okay.
Yeah.
And so I thought we were talking about dimensions of vector spaces, right?
We're pitting.
Oh,
We're pitting.
thank you. Yeah, I did not clarify that.
Without announcing that.
Pedagogy 101. Okay, so yeah, now we're talking about the dimensionality of an algebraic variety, which is different than a vector space. Sorry.
But
I'm going to move forward with this example. So we have an algebraic variety here, or no, rather a system of polynomials. And the first one is x squared plus y squared plus z squared equals 1. This corresponds to the unit sphere. And here you have a beautifully drawn unit sphere. And then, I drew this all kinds of terrible. This is x squared plus y squared equals 1/4, which really is the same as x squared plus, well, this is a circle with radius 1/2. And then if you embed that in the same space, then you're going to intersect this circle with radius 1/2 with the unit sphere. And the intersect of both of these shapes is our algebraic variety. And it turns out that's 2 circles. So our algebraic variety is a circle here and a circle here. So what's the dimensionality of that? That's like, it's not very intuitive.
Why 1?
Well,
Because I could pick a starting point in 1 circles.
Okay, yeah, it turns out that's true. But let me get there a little more circuitously. So the formal definition for the dimensionality of an algebraic variety is the dimensionality of the, what's it called? It's the tangent space to the variety. So really what you do, and it's the dimensionality of the tangent space to the variety only for regular points. And what's a regular point? A regular point is, really, it's just a point that's differentiable. So if you have a function that looks like this is not regular, because you can't differentiate there. But like here, you're good. Here, oh, there's the derivative. Look at these derivatives. Look at them go. So, okay, these are regular points. So we have the tangent space to our algebraic variety at any regular point. Okay, so take a point here. Oh, look at that. There's a tangent. Okay, cool. And then the tangent space, well, what's the tangent space? It's a vector space. So, bam, we go to our original definition, and we just use the number of basis vectors. So what's the number of basis vectors required for a line? It's 1. Thanks, Patrick. I asked. I totally had it coming to me. Okay. So, cool. Now we're going to get to something really weird and cool, because I cruised through this a little faster than I thought. Which is nice.
Pick on that.
There's actually, yes, which would make it a plane, which means it's 2-dimensional. And there is a reason, like outside of, if you go to the more general definition of a dimension, it's the number of coordinates required to differentiate any 2 points. So if you have this point here, and it's somewhere along our circumference of the circle, so we're representing it with an individual point x, and then you have another point here that is somewhere along, that's at the exact same x point, but on the different circle. How do we differentiate those? Well, you could say 0 or 1, or what you could do is like the very same thing we did with the cube, which is define the first circle as all values between 0 and 2 pi, and then this one as 2 pi to 4 pi.
Sure.
Or rather, 2 pi plus epsilon.
Or 4 pi, yeah.
It doesn't matter. Yeah, you get the point. So that's why it's 1-dimensional. And I was confused, and that just made sense. I was confused before this lecture.
That doesn't.
Yeah.
So this might be completely trivial, but if you have countably many circles, those are all 1-dimensional stuff.
It would be, because you can take this same thing, and if you have n many circles, then you just move this up to n 2n times pi.
Are countably many circles an algebraic variety?
Oh, that's a better question. No, your question was great. No, that's a good question too. I don't know. Okay, so I'm going to talk about, totally unrelated to that, I'm going to talk about inductive dimensions in topological space. So topological space is another space that I don't have time to define. And we want to define the dimensions of a topological space inductively, which is kind of cool. It's like a new way of going about defining the dimensionality. But the intuition behind this is that if you have a topological space, and just imagine Rn for now. Let's say we have R2. If you have a circle, which really is just the set of points that are equidistant to a given point, that we can call that S. That is going to have dimensionality of n minus 1. So we'll call it S of n minus 1, where 2 is n. And then, if you're in three-dimensional space, you'll notice that the sphere, you can flatten it out to a plane, so it has dimensionality of 2. So mathematicians were like, how can we formalize this to define the dimensionality of a topological space via a sphere? And that's exactly what they did. It's pretty cool. So let's start with the 0 case. Generally, with induction, it's like a ladder. You prove the 0 case, and then you say if it exists for n, it exists for n plus 1. So if n is arbitrary, we know it exists ad infinitum. So we have a space X, which is a topological space, and space X. And we're going to call the dimension of this, as defined by this process, the inductive dimension. And this is going to be, there's like a large inductive dimension and a small inductive dimension. We're dealing with the small inductive dimension. So say you have, by the way, we can have the empty set. The dimensionality of that, we're going to define as -1. And the reason for that is because when we have a line, we want the dimensionality, and we'll call this inductive dimensionality, to be 0. OK, so these are just formalities that we're blindly accepting. So for our space X, we can define the inductive dimensionality as the smallest n, such that for every point in our space, and then for every neighborhood in our space that contains that point, oh, I said neighborhood, I meant an open set. We also have an open set V, such that the closure of V is inside of our open set U, and the dimensionality inductive of V is less than or equal to n minus 1. So let's unpack this a little bit. V, think of this as the sphere. So, oh, does everyone know what a closure is? It's just, so like, if you have an open set, it doesn't have boundaries, but closure has boundaries. So you like say it ends here. And then U doesn't have a boundary. And then we have a point X. And just think of V as a sphere, n-dimensional sphere, that goes around point X, or centered at point X, and use an arbitrary open set in our space, and we take the minimum dimensionality of that. So really what I just did is I took a concept that you all understood and I confused you, but that's cool. So that's what I have prepared. Does anyone have any questions on this? OK, well, thank you.